Hello, my dear students. I am Sunira from Department of Physics, Government College, Madapalli. In this lecture, we will learn about floating point representation. This is part of electronics paper for 5th semester BSc Physics of University of Calicut. So, we can move on to floating point representation. In this floating point representation, a real number can be represented as a floating point. So, in this representation, the number has two parts. One part is called mantissa and the other part is called exponent. So, there are examples here. You can see here 13.2 into 10 raised to 29. In this number, 13.2 is called mantissa and 29 is called exponent. Okay. Similarly, 0.015 into 10 raised to 8. Here, 0.015 is called as mantissa and 8 is called as exponent. So, any real number can be represented as floating number which includes a mantissa and an exponent. Now, if the mantissa lies between 0.1 and 1, the number is said to be in normalized floating point notation. So, listen how we can normalize a floating point representation. If the mantissa lies between 0.1 and 1, the representation is called normalized floating point notation or representation. So, we can see here 13.2 into 10 raised to 29. Here the mantissa is greater than 1. So, this is not in the normalized form. But if we write this as 0.132 into 10 raised to 31, this is called normalized floating point representation. Similarly, the second example, here there is 0.015 into 10 raised to 8. Here, after the decimal point, there is 0. This is not in the normalized form. So, we can write like this 0.15 into 10 raised to 7. So, here this is called the normalized floating point representation. This mantissa part is always greater than 0.1 and less than 1. Okay. Here there is 1.91 into 10 raised to minus 29. This is also not in the normalized form because here 1.91. Okay. So we have to write this as 0.191 into 10 raised to minus 28. This is called normalized floating point representation. Now, we have to think about binary floating point numbers. So, in our previous slide, we discussed floating point numbers in the context of decimal system. Now, we can extend this concept to all number systems and especially to binary number system. So, in this form, in the normalized floating point representation, we can write the the real number as m into b raised to n. Here m represent mantissa and n represent the exponent. So mantissa should be 1 by b less than m less than 1. That means the mantissa should lies between 1 by b and 1. Okay, here B denotes the base of the number system. So, how many symbols are used? It is called base. In the case of binary system, b equal to 2. In the case of decimal system, b equal to b equal to yes, b equal to 10. The case of decimal system, b equal to 10. In the case of binary system, b equal to 2. So this mantissa should lies between 1 by b to 1 and n is called the exponent. Okay, hope that all of you get how to represent a binary floating point number. Examples for binary floating point numbers: 0.1101 into 2 raised to 10, 0.10 into 2 raised to minus 10. All these numbers are binary floating point numbers. So, in the case of decimal floating point number, the exponent is above the base. Okay, 10 raised to in the case of decimal system. Here this is the binary system. So you have 2 raised to 2 raised to 10, 2 raised to minus 10. These are the binary floating point number representations. Now, the case of binary floating point numbers, the certain examples are here: 0.001 into 2 raised to 13, 1.01 into 2 raised to 5. These are not in normalized form. Why? After the binary point, there are zeros. We already found that after binary point, there is no zeros for normalized form. Okay, so this is not in the normalized form. Similarly, here 1.01, this is also not in the binary form. Sorry, in the normalized form. This is not in the normalized form. This is also not in the normalized form. But these two numbers are in binary floating point numbers. So if we want to convert this to normalized form, you get this as 0.1 into 2 raised to 11 and 0.101 into 2 raised to 6. Hope that you get how to convert these floating point numbers into normalized form. This is done just like we do in the decimal system. But this time, in the case of binary system, the exponent is about 2, because 2 is the base of the number system. Okay, so in the normalized form, the binary point must be followed by 1. The binary, not number, the binary point must be followed by 1. Only exception to this rule is 0.0. Okay, so here you can write this is not number, here point. Okay, so to get the normalized form, the binary point must be followed by 1. Only exception to this rule is 0.0. Okay, hope that all of you understand how to make a floating point number in a normalized form. Okay, so now we have to move on to next slide. Now see how these numbers represent in a microprocessor or microcomputer. Suppose our microcomputer has 32-bit capacity. In our previous lecture, we learned about its capacity. If you mean 32-bit capacity, it means that simultaneously the processor can process 32 bits of data. Okay, 32 bits of data means 4 bytes of memory, because 8 bits are called 1 byte. So 32 bits of memory means 4 bytes of memory. So the floating point numbers are stored in 4 consecutive bytes of memory. Hope that you get what we have discussing here. Our processors are our processor has 32-bit capacity. So we have to use 4 consecutive memories. Each memory require 8 bits or 1 byte data. Okay, so 4 into 8, 32 bits. 4 bytes of memory used to represent a floating point number in the case of 32-bit processor. Okay, in this representation, the leftmost bit is used as the sign of the mantissa. Remember, the leftmost bit digit represents the sign of the mantissa. The next 23 bits are used for the magnitude of the mantissa and the last 8 bits for the biased exponent. Okay, so the next 23 bits are used for the magnitude of the mantissa. The magnitude of the mantissa. Okay, the leftmost bit is used as the sign of the mantissa. The next 23 bits are used for the magnitude of the mantissa and the last 8 bits for the biased exponent. Okay, so there are 4 bytes of memory. In this, the leftmost memory is used in the leftmost bit of the representation is used as the sign bit. After the 23 bits are used for representing the mantissa, the last 8 bits for used to represent the biased exponent. Okay, so what is this biased exponent? So we have to check what is biased exponent. Before that, I am showing here the 4 bytes of memories. See, M represent memory. We already discussed that we need 4 consecutive memories. First memory is M, then M plus 1, M plus 2 and M plus 3. So there are 4 memories. Each memory has 8 bit capacity. Okay, 1 byte. So 7 to 0 represents 8 bits of the memory. 8 bit memory M, M plus 1, M plus 2 and M plus 3. Okay, in this the leftmost bit, that means the bit in this position, represent sign bit of the mantissa. If 0 here, the mantissa is positive. If 1 here, the mantissa is negative. Okay, so the leftmost bit is 1 means the mantissa is negative. The leftmost bit is 0 means the mantissa is positive. Okay, after the next 23 bits, you can see here 8 plus 8 16, 16 plus 7 23. One bit is reserved for sign bit. Okay, so the next 23 bits used to represent the magnitude of the mantissa. Okay, finally the last 8 bits, the last memory used to represent the biased exponent. Okay, hope that you understand what we have done here. Here our processor has 32-bit capacity. So it needs 4 bytes of memory. So to represent the floating point number in a 32-bit processor, the device uses 4 consecutive memories. In this, the leftmost bit is exclusively for the sign bit of the mantissa. The next 23 bits used to represent the magnitude of the mantissa. The last 8 bits represent the exponent of the number, the floating number. This exponent is represented in the form of biased exponent. Okay, in the form of biased exponent. So, what is biased exponent? We already seen that The exponent can be positive or negative. So, in the case of 8 bits, we already discussed that 8 bits used to represent the exponent. So, if we use 1 bit for sign bit, we have only 7 bits to represent the magnitude of the exponent, right? That means you have to represent minus 2 raised to 7 minus 1. We already found that in the case of n bit representation, you have options 2 raised to n minus 1. Here also you have 2 raised to n minus 1. But in the negative side, the leftmost bit is 1. 1 means your exponent is negative. So here is minus. So 2 raised to 7 minus 1 minus 2 raised to 7 minus 1. You get minus 128. At the same time, if the sign bit is 0, you have plus 127. Okay, so this in this method, the 8-bit exponent, the leftmost bit of the 8-bit exponent is used to represent the sign bit of the exponent. Okay, so the positive and negative exponents and its processing becomes a tedious process. So instead of using these true exponents, we use biased exponents. So in the what is biased exponent? The true exponent is biased by adding a constant. The true exponent is biased by adding a constant. The modified exponent is called biased exponent. The modified exponent is represented in 8 bits because there is no sign bit now. See, so what we have to do? So we have to add a number such that the minimum exponent should be 0. So in our example, you can see that the minimum exponent is minus 128. So in order to make it 0, you have to add plus 128. Okay, so our biased exponent is always the true exponent plus 128. Okay, so in the biased exponent representation, the exponent varies from 0 to 255. The new exponent, the biased exponent varies from 0 to 255. In this case, no need of sign bit because we used biased exponent. Okay, so we move on to the next slide. So here we can try to do this representation. So convert 13.5 to binary and represent in floating point form. See, we already studied how to convert a decimal number to binary. Here what you want to do? All of you know that in this integer part you have to divide it by 2 successively and keep its reminders aside. If you write these reminders in the reverse order, you get its binary equivalent. But in the case of fractional part, we have to multiply this fraction part with 2 and take its integer part. Continue this process until all numbers become 0 or if we get the sufficient accuracy. We have studied all these in our previous lecture. Okay, so if you convert this number 13.5 to binary, equivalent to 13, you get 1101. 1101. Okay, base 2. This is for binary. In the fractional part, 0.5 into 2, this is equal to 1. So, here the integer part is 1 and the fraction is 0. So, there is no more multiplication needed because fractional part goes to 0. Okay, so we get 0.5 base 10 equal to 0.1 base 2. Okay, this is binary point, this is decimal point. So if we add these two, you get 13.5 base 10 is equal to 1101.1 base 2. See, but we already learned that this is not in a normalized representation. So we can make this the form of a floating point representation just like a normalized form. Okay, so 0.11011 into 2 raised to 4 represent its floating point representation. Normalized floating point representation. Okay. So in this problem, the mantissa is 11011. The exponent, the true exponent is 4. So we have to represent this in the form of biased exponent. So what we have to do, the representation of 32-bit processor, we have to add 128 to the exponent. So you get 128 plus 4, 132. So the biased exponent is 132. Now we can write this mantissa and this exponent in our binary notation in the 4 bytes of the memory. Okay, so here there is 23 bits equivalent of mantissa. 23 bits equivalent. So we already have only 5 bits, 11011. So we write here 11011. The leftmost bit is reserved for sign bit. Actually here comes 0 because our number is positive 13.5. So here comes 0. After that 11011. All other 23 bits, in the total 23 bits from here to here, in that 23 bits we have 5 bits as our solution 11011. All remaining 18 bits put as 0 0 0 0 0 like this. Okay, so up to 3 consecutive memories used to represent the mantissa part. Okay, so you get the mantissa part as 11011 0 0 0 0 0 0 0 0 etc. up to the 23 bits. Okay, now the last 8 bits exclusively for 132. 132 in binary form represent like this 100000100. So altogether this 13.5 is represented in a 32-bit microcomputer or processor as this 011 011 00000000000000000000, then 100000100. Okay, hope that you understand how to write a floating point in this format. Okay, so we move on to next part. So in this case, we found that the representation of floating point is already we discussed such that excess 128 code because in the biased exponent form. So in order to make the exponent independent of the sign minus or plus, we just add a 128 to the exponent to make it varies from 0 to 255. So this representation is called base to excess 128 code. Base to excess 128 code. Okay. So in this method, we can represent a negative number such that its leftmost digit is representing the 1 to represent the negative number. Okay, then the next 23 bits for its magnitude, just like we do in all numbers. Find the representation of the absolute value of the number. Then we have to take its 2's complement or 1's complement, whatever is used of the mantissa and sign bit together. Hope that you understand how to convert a negative number. In the case of a negative mantissa, the leftmost bit is 1. We already found it. The next 23 bits represent in terms of its the next 23 bits used to represent the 2's complement of the binary representation. So the first we have to find out the binary representation of its absolute value. Then from that we can find out its 2's complement. But if you find out the 2's complement, you have to include the sign bit also together. Including the sign bit, we have to find out its 2's complement or 1's complement depending on the processor, which type of processor we use. Okay, in this way we can represent a negative mantissa in this floating point representation. So here there is example minus 13.5. So we already found that 13.5 can be written as 1101.1. In this case, the mantissa part is 11011. 11011. The exponent part is 2 into 2 raised to 4. Okay, so 4, true exponent is 4 plus 128. So the biased exponent is 132. So if you found its 1's complement, you get 00100. 00100. Just changing ones to zeros and zeros to ones gives you its 1's complement. We learned it in our last class. Then to get 2's complement from this, we have to add this 1 to this number 0010101. Okay, now adding zeros to the right to reach the enough number of bits like this. 1 reserved for negative number, then 0010100. These all are up to this much. Zeros put here to get enough number of bits, 23 bits. Now the power, the exponent. In this case, the exponent is 132 itself. So we have the same exponent as we already found. The difference lies here in this part. Okay. Now we have to think about its accuracy and range. So here, the sign of a floating point number depends on the sign of its mantissa. As the exponent increases, the magnitude of the floating point number increases. Similarly, the case of 8-bit representation for the exponent, the maximum true value is 1 plus 127 and minimum value is minus 128. Okay, so in the case of a 32-bit representation, the largest floating point number is 0 followed by all ones, followed by the true exponent of plus 127. This is the maximum number in this case. So we have to check just its magnitude, the order of magnitude of the maximum number in this system. So we found that the true exponent, its maximum value is plus 127. So 2 raised to 127 must be equivalent to 10 raised to x to get its order in decimal. So taking logarithm, you can find that x equal to 38. So the order of the magnitude is 10 raised to 38. If the sign bit is negative, the number becomes more negative for increasing the exponent. Okay. Now, if the mantissa is positive and the exponent is negative, the number decreases towards 0. So, we have found out the minimum number. The minimum positive number occurs when exponent reaches minus 128. So, we can find out the minimum order of magnitude just like we done for maximum. So, here we can write 2 raised to minus 128 equal to 10 raised to x, where this x equal to minus 38. So, the minimum positive number is of the order of 10 raised to minus 38. Now, what is its range? Range is defined as the range of values between the minimum positive floating point number and the maximum positive floating point number. So, in this case, in the 8-bit case, it is lies between 10 raised to minus 38 to 10 raised to plus 38, or we can write it as 10 raised to plus or minus 38. So what is the range? The range is defined as the minimum positive floating point number to the maximum positive floating point number. Now about its accuracy. We we have to take log and anti-log in this conversion process. So it reduces the accuracy. For example, suppose we have to take logarithm of 583.422 and take its anti-log. If you take logarithm and take anti-log, you get this 583.400, not 583.422. So what happens? So our answer is not wrong. It is correct up to 4 decimal places. This digit is correct up to 4 digits, 4 places. So the decimal equivalent of the 23 bits, that means the mantissa part, is 2 raised to 23, or in this case its decimal equivalent is x equal to 6.9. So we can be certain of 6.9 digits accuracy in the case of 23 bits. Okay, now but 6.9 digits gives only an upper limit on the number of digits that may be correctly represented. But it doesn't mean that every number less than this correctly represent, because we already found in a problem in our previous lecture that the conversion itself generates a limit to the accuracy. The user can't do anything with these type of corrections. Okay, so there are some built-in inaccuracy in our this conversion process. For example, see 0.4 in decimal is converted to its equivalent binary. But we can see that this as already we found that if we multiply this fraction with the 2 and takes its integer part. So here 0.4 into 2 equal to 0.8. So its integer part is 0. Then again multiplying this with fraction 0.8 into 2 1.6. Integer part is 1 but its fraction is 0.6. Again multiplying with the 2 you get 1.2. Integer part is 1 and fraction 0.2. 0.2 into 2 equal to 0.4. Again comes 0 and this process continues. But suppose this process cannot be end after some time. So we have to limit it somewhere. Suppose we done this conversion up to this much. Okay, so we have 0.4 base 10 equal to 0.0110 binary. If you convert this binary in reverse order to this 0.4, this its equivalent decimal, you can see that this number is equivalent to 0.375 in the decimal system. But we convert 0.4. So here there is a correction, slight error in this conversion process. If we add more and more numbers by continuing this process, this term approaches to 0.4. Okay, that means there is an error generated by the conversion. So in this floating point representation, it has certain limitation in its range and accuracy. In its range and in its accuracy. Okay, so hope that all of you understand what is this floating point representation. So real numbers can represent in the form of floating point. In that case, there are two parts for the number. One is called mantissa and the other one is called exponent. So all these numbers stored in a processor, microprocessor or microcomputer within consecutive memories. Usually each memory has 8-bit capacity. So we need 32 bits. We need 4 bytes, 4 memories. 4 bytes. We need 4 bytes. That means 4 memories. In these 4 memories, first 3 are used to represent mantissa and the last one, the fourth one is used to represent the exponent. Okay, so in the first 3, the leftmost bit is used to represent the sign of the mantissa. If it is 0, mantissa is positive. If it is 1, the mantissa is negative. Similarly, in the last 8 bits used to represent exponent, which can be positive or negative. So there also we can use the leftmost bit as sign bit. In the case of last 8 bits, the leftmost bit can be used as sign bit. So in that case, the problem is the exponent varies between minus and plus, negative and positive. So in order to reduce these type of problems, we can use these 8 bits to represent the number just by adding a constant to the exponent. That representation is called biased exponent form. Biased exponent form. So in this representation, it has built-in accuracy limit and range, which have discussed here very elaborately. So I think that you can learn this well after listening to the lecture very well. If you have any doubt, please contact me through my WhatsApp. After hearing or listening all these things, you can move on to next slide where I have given certain questions as assignments like this. Okay, then try to find out answers to these assignment questions. If you get answer, you can make sure that you learn very well all the things in these slides. Okay, so thank you.